Welcome to the lecture. Today we are going to start with a new topic, which is multiple linear regression modeling. So, if you recall, we started with a simple linear regression model where we consider the situation where the outcome is going to be dependent only on one independent variable. Now we are going to extend it. In practice, this situation is more realistic. The outcomes usually depends on more than one factors or more than one variables. So we are going to consider here a situation where the outcome is going to depend on more than one independent variables. Now, the situation is the following, that in the case of simple linear regression modeling, we have developed many concepts and I have tried to explain you their utility and their interpretation. The same concept, the same interpretation will be brought forward in the case of multiple linear regression modeling. So, it is my request that before you start with multiple linear regression model, it is very important that you are clear about all the concepts of the simple linear regression model. So here we believe that the outcome which we had denoted as y, this depends on more than one independent variables. And earlier we had discussed the simple linear regression model, that was beta 0 plus beta 1 x plus epsilon. Now, here we assume that there are more than one independent variables, and suppose there are k independent variables. And we denote them by here, say x1, x2 up to here xk. So, the same model which we have considered in the case of simple linear regression model, this can be extended to the case when there are more than one independent variables, and this can be written as, say, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 up to here, say, beta k xk plus epsilon. Now, about the interpretation, means earlier we had said that this beta 0 is the intercept term, and this remains the same here. And we say now that beta 1, beta 2, this beta k, they are the regression coefficients associated with x1, x2, xk respectively. Right. So, essentially this beta j is the regression coefficient associated with jth explanatory variable xj, right. Okay. And epsilon equals to the same thing as our random error. Now, in this case, the role of random errors becomes quite important. When we are dealing with a real life situation, the first step in doing a regression modeling is to identify what are my independent variables, or what are the variables which are going to affect the outcome, y. When we try to do so, Sometimes it is possible to obtain the observations on those variables, and sometimes it becomes difficult to obtain the observations on the independent variable. For example, if I take a variable like taste or intelligence, it is difficult to obtain the numerical values on the variables like taste or say intelligence. The intelligence is usually measured by IQ scores, but they are again a sort of indirect measure of intelligence. Similarly, there are some variables which may not be very important, or they may have a very small effect on the outcome y. Based on that, sometimes we try to consider them, or sometimes we do not consider them. On the other hand, in case if the number of explanatory variables becomes very, very large, the situation becomes more critical, and in that case we would try to retain only the important variables which are trying to affect the outcome y. So, there will be many situations which are beyond our control, and epsilon denotes the joint effect of all such factors which are beyond our control. So, epsilon is like a basket in which we try to put all those things which are beyond our control, right. Okay. So, this epsilon essentially depicts the, or it reflects the difference between observed and fitted model. And this idea goes exactly on the same lines what we had done in the case of simple linear regression model, right. Now, the situations in which we can use this multiple linear regression model are many. First of all, I try to extend the same example which I had considered in the case of simple linear regression model. In the case of simple linear regression model, I had taken an example of yield of a crop, where I denoted y as the yield of crop, and we had taken x as the quantity of fertilizer. But do you really think that the yield of a crop depends only on the quantity of fertilizer? But it depends on say several other factors. So, now we have an opportunity to incorporate all those important factors which are affecting the yield of a crop. For example, the first factor I can write down x1, which is my quantity of fertilizer. Similarly, x2 can be level of irrigation. Third thing can be the quantity of seeds. X4 can be rainfall, and similarly you can identify some more important factors which are affecting the yield of a crop. So, now under these things we have to now develop a multiple linear regression model. Now, you may recall that in the case of simple linear regression model, the first step what we had defined for a linear regression model is to obtain data. And in case of simple linear regression model, we had obtained the data on y and x. We conducted an experiment, we provided the value of x, and then we had observed the values of y, and this experiment was repeated n times. The same thing has to be extended here also, that that we have to conduct the experiment, provide the value of the values of x1, x2, xk, and then record the outcome y. So, if you try to see, means earlier we had a set of observations like xi, yi, But now we are going to have a set of observation which is something like say xi1, xi2 and up to here say the xik and yi, and I goes from here 1 to n in case if I try to repeat the observations n times, right. So, as earlier we had assumed that all the observations, they will also follow the same model. And in the case of simple linear regression model, we had the model y is equal to beta 0 plus beta 1 x plus epsilon, and we assume that all observations xi, yi, they are going to follow the same model and they will satisfy yi is equal to beta 0 plus beta 1 xi plus epsilon I. Now, we have to extend the same definition in the case of multiple linear regression model. So, let us try to first set up our model. So, we consider the model setup. So, it is as simple as that: conduct experiment n times, and we are going to obtain here the values of here y and x1, x2 up to here xk. So, this is how we are going to obtain our values. Suppose I conduct the experiment and I give x1 a value say x11, x2 a value x12 and xk a value x1k. And based on these values, we try to observe the outcome y, and we denote it as say here y1. So, this is our first set of observation, right. And similarly, we try to obtain the second set of observation, that we try to give the value x1 as say x21, x2 the value x22 and say xk the value x2k, and we obtain the observation y2. So, this gives us the second set of observation, and we continue with this thing, and finally we obtain the nth set of observation by giving x1, x2, xk the values xn1, xn2, xnk, and we observe the value here yn. So, this is the nth set of observation, right. What does this actually mean? For example, if I try to take the same example of yield of crop. So, for example, if I say this here x1 is my quantity of fertilizer and say here x2 is my irrigation level and x3 is my suppose here seeds, right. So, what we try to do here, suppose I try to give 2 kilogram of fertilizer and say 10 centimeters of irrigation, and suppose I use 1 kg of seeds, and based on that we try to observe the yield, and we get suppose here 40 kg of yield. So, this is my x11, this is my here x12, this is my here x13, and this is your here y1. And similarly, I can repeat this experiment and I can take say here say I use 3 kg of fertilizer, say this 15 centimeters of irrigation, 2 kilogram of yields, and based on that we observe suppose 50 kilogram of yield. So, this will be denoted your here as say x21, this will be your x22, this will be x23, and this will be your here y2. And similarly, we try to repeat this experiment n times and we obtain n sets of observation. Okay. So, now if you see, we have here a model which is y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus up to here beta k xk plus epsilon, right. Okay. Now, we assume that each set of observation satisfies this model of observations, the model. So, this means I can express for the first observation, I can write that y 1 is equal to beta 0 plus beta 1 x 1 1 plus beta 2 x 1 2 plus beta k x 1 k plus epsilon 1. Similarly, for the second observation, I can write down the model as a beta 0 plus beta 1 x 2 1 plus beta 2 x 2 2 plus beta k x 2 k plus epsilon 2, and so on. For the nth observation, I can write down y n is equal to beta 0 plus beta 1 x n 1 plus beta 2 x n 2 plus beta k x n k plus epsilon n. Right. So, essentially if you see here, we have got here n equations. Now, these n equations can be expressed in the form of vectors and matrix. So, we can write down these n equations as follows. That let us try to define here a vector of y 1 y 2 y n, and this is equal to. So, we define here one matrix, and here we define here a vector beta 0, beta 1, beta 2 up to here, say here beta k, and based on that the first row of this matrix will be 1 x 1 1 x 1 2 up to here x 1 k, and the second row will be 1 x 2 1 x 2 2 x 2 k, and similarly the third row will be x 3 1 x 3 2 up to here x 3 k, and this will continue up to here the x n 1 x n 2 up to here x n k, and plus epsilon 1 epsilon 2 epsilon 3 up to here epsilon n. Right. Okay. So, now I can denote this vector as a here y, right, and this matrix here as a x, this vector here as a beta, and this vector here as a epsilon. So, I can write down the entire model as a here y is equal to x beta plus epsilon. Now, we try to observe here that this first column is here only 1 1 1 1 1. This is indicating the intercept term. This can be made a little bit more general, that I can write my model in general as say here y is equal to x beta plus epsilon, and where I can say that x is going to be something like x 1 1 x 1 2 x 1 k, x 2 1 x 2 2 x 2 k, x n 1 x n 2 x n k. And in case if I want to consider the intercept term in the model, then the first column of the x matrix has to be made 1 1 1 1 1, and in case if I do not need an intercept term in the model, this x matrix will remain as such. So, this is a very general form, the general form, and in which we assume that y is a say n cross 1 vector of observations on steady variable or let me call say response variable sometime. X is a n cross k matrix of n observations on each of the k independent variables x1, x2, xk. Beta is going to be something like beta 1, beta 2 and here say beta k prime. This is going to be a k cross 1 vector of regression coefficients associated with x1, x2, xk. Okay. And epsilon here is as usual epsilon 1, epsilon 2, say epsilon n, which is a n cross 1 vector of random errors. Okay, because for the sake of completeness, I can also write here y here as say y1, y2, say here yn transpose, right. Now the question is that in case if I want to have intercept come in the model, then what I have to do? Intercept term, take first column of X matrix to be 1, 1, say 1, right. And then correspondingly this beta 1 will become the interceptor. Right. So now onwards we will start with the model y equal to x beta plus epsilon, and we will not bother whether there is an intercept term or not. In case if I want an intercept term, I simply have to write the first column of X matrix to be 1, 1, 1, 1, 1. Otherwise, we will simply continue with the X matrix as a matrix of the observation obtained on the explanatory variable. Okay. So, you may now recall that in case of simple linear regression model, we had made certain assumption about the model. The similar assumptions we are going to make for the multiple linear regression model also. So, if you remember the first assumption what we had made was that expected value of epsilon I is 0. Now, in case of multiple linear regression model, we do not have one epsilon I, but we have a vector of epsilon i's. So, I can assume that expected value of epsilon is equal to null vector. The interpretation part of this thing that we already had discussed in the case of simple linear regression model. The second assumption is about the variance covariance matrix. So, we assume that variance covariance matrix of epsilon, which is the same as expected value of epsilon, epsilon prime, this we assume is sigma square I n. So, it is something like this, it will look like this. The diagonal elements, they are going to denote the variances of epsilon 1, epsilon 2, epsilon n, and the off diagonal elements they are going to denote the covariance between epsilon I n, epsilon j, so which are 0. So, again this is the same assumption that all epsilon i's are say identically and independently distributed. Okay. So, we can see here from this matrix that we are assuming that all epsilon 1, epsilon 2, epsilon n, they are having the same variance sigma square and they are mutually independent of each other. Right. The third assumption which we are going to make here is that rank of X matrix is going to be the k. And remember, k is the number of independent variable. So, we essentially we assume that this is a full column rank. Right. The advantage of making this assumption will be clear to you in the next lecture when we go for the estimation of parameters. Right. The next assumption we make is that X is a non-stochastic matrix. You may recall that a similar assumption was also made in case of simple linear regression model, where we assume that X is a fixed quantity. It is a non-stochastic random variable. So similarly here we are trying to make it more general. We have now not one variable but more than one variable. So we are trying to extend the same assumption of the simple linear regression model to a more general case for all the k independent variables. Okay. And the last assumption what we make here, that epsilons are following a multivariate normal distribution with null vector and covariance matrix sigma I square in. Right. So this assumption is again similar to the assumption what we made in the case of simple linear regression model. There we assume that that epsilon i's are following a normal distribution, a univariate normal distribution with mean 0 and variance sigma I square. Now we are trying to extend it for all epsilon 1, epsilon 2, epsilon n. Means again I would like to emphasize that the utility of normal distribution comes into picture when we consider the maximum likelihood estimation of the parameters, or when we go for the test of hypothesis and confidence interval estimation. Next we come on the aspect of interpretation of these regression parameters. So we have considered here a model y is equal to beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon, and now we have assumed that expected value of epsilon is equal to a null vector. So I can write down expected value of y to be here beta 1 x1 plus beta 2 x2 plus beta k xk. And now here itself you can see the utility of assuming that xk's are non-stochastic. Another advantage of assuming that that x1, x2, xk are non-stochastic is that the outcome of the experiment will not be dependent on the values of x1, x2, xk. So if somebody is conducting an experiment in city number 1 and somebody is collecting the observation in city number 2 and somebody else is collecting the observation in city number 3, then whatever the analysis we are going to obtain on the basis of collected set of data, that is not going to dependent on the city number 1, city number 2 or city number 3, right, but that will be valid for everyone. So now based on this, if I try to find out the partial derivative of expected value of y with respect to here certain variable, say here xj, this comes out to be beta j, right. So you can see here that this beta j is nothing but the rate of change in the mean value of y with respect to jth explanatory variable. So this essentially denotes the change in the mean value of y when jth explanatory variable changes by 1 unit. And if you try to recall, this is the similar interpretation as in the case of simple linear regression model. So, whatever interpretation I had given to beta 1 in case of simple regression model, that is now extended to beta 1, beta 2, beta k. Now, in case if you say that what is the interpretation of having an intercept term in the model. So, in case if I try to consider here an intercept term, so I simply have to take here all values of x1 to be 1. In this case, the model will become expected value of y beta 1 plus beta 2 x2 plus here say beta k x k, right. So, if I try to take all x2 x3 and all other values of x2 x3 xk to be 0, then expected value of y becomes nothing but beta 1. So, in this case also the intercept term will denote the mean value of y when all independent variables take value 0. And again, this is the same interpretation that we had given in the case of simple linear regression model. There I considered only one variable x to be 0. Now I am saying that all x1, x2, xk they are going to take the value 0. So, we have completed here the description of the model. In the next lecture, we will consider the estimation of the model parameters. Till then, goodbye.